Hey everybody, welcome to our penultimate video in Statistics 2 for the 2019-2020 school year. For those of you who've stuck with us through all of these videos and assignments, I just want to say thank you, and I hope that you've been getting a lot out of this course. And hopefully we'll be looking at numbers and the way people around you use numbers a little differently from here on out. So today we're going to be talking about testing differences between proportions. So let's first have a recap of what we have done up to this point. We've talked about confidence intervals, which have the purpose of using a statistic to estimate a parameter. There's some value we don't know. We collect a sample. We use its value to estimate the population's value. For proportions, confidence intervals had this formula, and for means, confidence intervals had this formula. And one of the big differences is that proportions use the normal curve, which is why there's a z, but means, since we typically don't know the standard deviation of the parent, uses the t-curve, so there's a t-star there. Then we had inference tests, which test a statistic against a given parameter. So we hear that somebody thinks that the true proportion of something or the true mean of something is a given value. We want to see if we have evidence that that's true. So proportions use normal CDF because, again, that proportions use the normal curve, and means use TCDF, which we discussed last week because they use the t-distribution. But what are we going to be actually doing now? So instead of testing using a statistic to estimate a parameter, or using a statistic to test a parameter, we're going to be using a statistic to test against another statistic. And that's called inference on differences. And if that seems a little confusing, you've probably actually seen this happen many times. At least you've seen statistics compared with other statistics. It's very common. It's unfortunately, though, what's not necessarily common is that it's done correctly. So this week we'll be looking at differences between two proportions, and finally next week in our final video we'll be looking at the differences between two means. So suppose you see a headline, and I apologize for the topicality, but this is what I thought of. Revealed: more New York residents want to reopen than CT residents. You actually get interested, so you look further in the article, and it says that 45% of New York residents want to reopen versus 38% of Connecticut residents. Now at this point, if you've been following along the course, this should immediately raise a red flag to you, because you know they didn't survey everybody in New York and everybody in Connecticut, so where are these numbers actually coming from? When you do a little more digging in the article, you find out that they surveyed 200 New York residents and 90 of them said they wanted to reopen. That's where they got 45%. And they surveyed 100 Connecticut residents and 38 of them said they wanted to reopen. So that's where they got the 38%. So the question we're going to raise is between these two surveys, does this actually provide evidence that more New York residents want to reopen compared to Connecticut residents? So let's talk about how we would actually begin the inference process when we're actually comparing two statistics. Both of their proportions came from a sample. So we need to define what we're going to be talking about. So if you recall, we use P's for proportions. So we're going to let P1 be the true proportion of New York residents wanting to reopen, and P2 be the true proportion of Connecticut residents wanting to reopen. So those are parameters that we don't know. But we're going to define a new parameter, P1 minus P2, which will be the difference in the true proportions. So this will give us our null and alternative hypothesis. Our null hypothesis essentially is that the two proportions are the same. We write that as P1 minus P2 equals 0, which would be true if P1 and P2 are the same proportion. The alternative hypothesis is P1 minus P2 is greater than 0. So note that that's directional, and it's directional because the question was whether or not we have evidence that the proportion of New York residents wanting to reopen is greater than that of the true proportion of Connecticut residents. Our statistic is going to be the difference in the proportions that we got, and it was 45% minus 38%, which gives us 0.07 as our sample statistic here. And the problem did not give us an alpha level, so for our purposes we'll say it's 0.05, which is a good default alpha level for inference if you're not given an alpha level. So the big question is what our sampling distribution will look like, because that will determine how we find our p-value. So our shape will be normal. We are using proportions, so that will use the normal curve. We assume the mean of the sampling distribution is the same as our null hypothesis value, as always, which in this case is 0. But what I want to bring your attention to is a new way of computing the standard deviation, and it probably looks a lot more complicated than what we've done in the past. For one thing, there's this new thing that says p pooled. So let's talk about that down here. So p pooled is what we call the pooled proportion. So what we literally do is we take the two proportions that we got from our samples and we put them together as a single proportion. And why do we do that? Because according to our null hypothesis, we're actually going to be assuming that both of the proportions are coming from the same population. That's actually what we're testing against. Do these proportions seem to come from the same parent population? So we kind of just put them together and pretend they are the same parent population. And if you look at the standard deviation that uses the pooled proportion, it looks a lot more complicated than ones we've done previously. But if you look at it closely, you kind of see the p times 1 minus p over n that we've used for inference on proportions and confidence intervals on proportions. It's just that that happens twice. And the reason why it happens twice is because we had two groups that we pulled from. So we're actually really combining the standard deviations of what would be the two separate proportions. So now we're going to actually plug in our values, so hopefully I can convince you that this isn't actually as complicated as it may look at first. So we know the mean is 0 from our null hypothesis, but we need to compute our pooled proportion. Now we're told that it was 90 New York residents and 38 Connecticut residents. That gives us our numerator of 128. There's also 200 total New York residents surveyed and 100 total Connecticut residents surveyed. That gives us our denominator of 300. So we're just taking the numerators and denominators of the two proportions and just putting them together and finding that new value, which is 0.427. Note that that proportion is somewhere in between the 45% and 38% that we got from the two samples, which makes sense. If we put them together, we should get a fraction somewhere in between. Now we actually have to compute the standard deviation, and this is what it's going to look like. So we have our pooled proportion of 0.427, and that's going in the two parts of the standard deviation calculation. So if we put that standard deviation into our calculator, we get a value of 0.0606. Now we have to remember that because our alternative hypothesis is right-tailed, p1 minus p2 is greater than 0, our statistic is a lower bound. So since we're using the normal curve, we put in normal CDF. Our lower bound is 0.07, which is our statistic. Right bound is infinity. We'll put that in as E99. The mean is 0, and our standard deviation is 0.0606. This will give us our p-value of 0.124. And that p-value of 0.124 is greater than our alpha value of 0.05, which means we do not have significant evidence that the true proportion of New York residents that want to reopen is greater than the true proportion of Connecticut residents that want to reopen. So even though some journalists might have done some very preliminary survey research, they didn't actually test to see if the proportions they got were actually significantly different. So there really was no significant evidence from that sample alone that the true proportions are actually different. And this is something we have to be careful of, and this is why we have statistics. This helps us make better sense of doing this work. Let's do one more example to hopefully make sure that we got the idea. So let's say a psychologist is studying gender differences in a task of balance and coordination. And she's able to work with 70 women and 50 men who each attempted the task. And she finds that 52 of the women and 26 of the men were able to complete the task. So obviously our question is, does the researcher have evidence at the alpha equals 0.05 level that the true proportions of women and men who are able to complete the task are different? Now one thing you should note here is it says different. It's not saying that one is greater than or less than the other, which, if you recall from our previous lessons, tells us this will be a non-directional test. So let's start defining our parameters. We'll again let P1 be the true proportion of women able to complete the task, and P2 will be the true proportion of men able to complete the task. our hypotheses. Our null hypothesis is P1 minus P2 equals 0, and that's always going to be your null hypothesis for this type of work. And our alternative hypothesis, P1 minus P2, is not 0. Again, non-directional task because the question was to find evidence that they're different. Our statistic is going to be the difference in the actual proportions. For women, it was 52 out of 70, which comes out to about 0.743. For the men, it came out to 26 out of 50, which is 0.52. The difference in those proportions is 0.223, so that's going to be our sample statistic. We're going to pool our proportions so that we can compute the standard deviation. Again, our numerator is the 52 from the women and 26 from the men. Our denominator is 70 from the women and 50 from the men, and that's going to give us our pooled proportion of 0.65. We could use that then to compute the standard deviation that we need, and here it is. So we have the square root of 0.65 times 1 minus 0.65 over 70, plus 0.65 times 1 minus 0.65 over 50. So you want to make sure that you are plugging that into your calculator correctly and getting the same values that I got, because that gives us a standard deviation of about 0.0883. Now our test is non-directional, but we see that the statistic, which was 0.223, is greater than 0, so we're testing an upper tail. So that means our statistic will be a lower bound, and positive infinity will be our upper bound. So we do normal CDF again. 0.223s are lower, infinities are upper, 0 is our mean, and 0.0883 is our standard deviation. And that's going to give us 0.0058. But we have to remember that our test is non-directional, which is going to make our p-value double what we got from the normal CDF because we have to incorporate that lower tail. So the actual p-value is 0.0116. Now, our p-value is 0.0116, which is less than our alpha level that was stated earlier of 0.05. And because of that, we're going to say that the researcher does have significant evidence that the true proportion of females and males able to complete the task are different. Now, obviously, if we used an alpha level of 0.01, we would not have been able to reject the null hypothesis, but that's why it's important to have an alpha level stated ahead of time so that we know how best to interpret our p-value. So I hope that this made sense. We have a few new mechanics in this lesson, particularly pooling our proportions and a slightly different standard deviation, but I hope you also saw that a lot of what we're doing is very similar. We have null and alternative hypotheses, we're using normal CDF because it's inference on proportions, and at the end of the day we're comparing a p-value to an alpha and drawing a conclusion, which kind of is how we do any type of inference test. So I hope this made sense for you and that you can go on to complete the practice exercises. Next week we'll do inference on means, and that will close us out for the year. So I'm Mr. Hill, and I hope you have a good day and rest of your week.